today we have Matthias Gerstgrasser. I hope I didn't say that name too badly. And he will be presenting recent contribution of his titled Selectively Sharing Experience Improves Multi-Agent Reinforcement Learning. Matthias is a postdoc jointly at Stanford with D. Young and at Harvard with David Parks, working on multi-agent reinforcement learning. His research interest is in combining deep reinforcement learning with insights from game theory and mechanism design, and on building systems that foster cooperation. He previously completed his PhD at Oxford, advised by Paul Goldberg and Elias Kotsoubias. His current work is a collaboration with Sarah Keren and Danino and Ateknian. So thank you very much, Matthias, for being here today, and we look forward to your talk. Thank you.
Thank you. I'll get started then. Let me share. I take it you can see slides now?
Yes, all good.
Perfect. Okay. So yeah, thanks for the introduction. As mentioned, this is work with Tom Danino and Sarah Keren, who are both here today as well. So when we have questions and discussions later, I hope you can meet them as well. This is a paper we had at NeurIPS this year together on selectively sharing experiences in multi-agent RL. Okay, so for some background and sort of how we got to this paper, we were looking at multi-agent RL and we're realizing that usually this is considered a hard problem. Sort of the presence of other agents is generally considered to make the problem harder than if you're just by yourself, because other agents create non-stationarity and some other issues. But we were thinking, can other agents also be an advantage that you can leverage, that can actually make the problem easier and that can be an advantage to you? And in particular, what we were thinking, suppose I'm one of the agents, I'm exploring the environment, and I realize something new. For instance, I realize if I press the button over there, the light goes on. Wouldn't it be nice if I could somehow, once I realize this connection between pressing the button and the light going on, could I tell everybody else about it? So that everybody else can now also know that if they press the button, the light goes on, for instance. So really the idea here is, can we let agents share some of the experiences that they sample in the environment? And can that then help other agents learn without having to sample those same experiences themselves? So this might be especially useful if it's something that's unexpected, but maybe not very common, so that would usually require a lot of random exploration until you actually find this thing in the environment. Wouldn't it be nice if we could only have one agent have to find that, and then everybody else can learn from it as well? So that's really the idea. The key question then is, which experiences do you share? And here we had an idea that's very simple. We used the TD error that's already used in single agent DQN with prioritized experience replay as a proxy for how relevant an experience is. And we just use this same heuristic to decide which experiences to share. TD error is basically the difference between what your current policy expected to happen and what actually happened informally. So the bigger the TD error, the worse, the more far off your prediction was, and sort of the more unexpected it was what actually happened. So that's our idea. We call it selective multi-agent prioritized experienced relay. It's obviously, we call it short and super. Obviously, it's a little bit of an homage to PER, prioritized experience replay, because we use the same TD error. Otherwise, it's not directly related though. So it's not just an extension of PER. It's kind of a separate scheme. You can combine it with PER. You could use it without PER. We also tried this to make this a little bit more clearer with this pun we have at the end here, where ours is called relay instead of replay, but maybe that was a bit too subtle. I don't know if any of the reviewers got that. So the idea is each agent, as they sample from the environment, they share some fraction of their highest TD error experiences. And those experiences then get directly inserted into everybody else's replay buffer. So if I find something in the environment, I put it into my own replay buffer, but then I also look at it and look at whether it's very unexpected. If it was very unexpected, I just send it out on a shared communications channel, and then everybody else puts it directly into their own replay buffer as well. By extension, it also means we are mainly focusing on algorithms that use a replay buffer, so we build all of this on top of DQN as well. One small point I want to make before we go any further is that this is related in a way to communication multi-agent RL, but it's kind of doing the opposite what most communication literature does. So there's a lot of literature out there on learning to communicate and emergent communications and so on. That's not what we're doing here. We're kind of doing the opposite. We're using communication to speed up the learning process, but the communication is hard-coded. We're not like learning how to communicate. That's just part of the algorithm. And the second interesting thing about what we're doing here is that it's kind of similar to centralized training, decentralized execution, but not quite, in the sense that training is also mostly decentralized. We just need a little bit of a communications channel during training, but in principle, the training is decentralized. Not entirely, we need this communications channel, but it's not like you really need to train in a centralized way. In principle, you could do this decentralized with communication. Before we go into results, I also briefly want to contrast this to a previous paper from your group called SEAC, Shared Experience Actor Critic. So how is super different from what SEAC does? And the big difference is really selective sharing of experiences. So in SEAC, the entire trajectory, all the experiences were shared between all the agents. The main difference on a technical level with super is that we only share a small fraction of experiences. And that's partly because we're motivated, I think, in a slightly different way. We really were thinking about real world applications. So we're low bandwidth, but decentralized training is part of it. But also we were really focused on adapting just to unexpected things. So for instance, to a sim to real gap, you can imagine if you train in a simulator and then you deploy to the real world, some things are going to be as you expected them to be from the simulator, and some other things are going to be unexpected. So we really wanted an algorithm that really focuses on these unexpected changes. Or for instance, if you are already deploying in the real world, but you keep training in the real world and then something in the real world changes. We want to be able to focus specifically on these unexpected changes to adapt to them faster. And we were really thinking, for instance, applications like, suppose you have self-driving cars. You might train them before you deploy them, but then once they're out in the real world, you probably want to keep training as they adapt to things happening in the real world. And it might not always be possible to just record every single car 24/7 and train on all of it. Ideally, you want to be able to decide locally what part of what you see in the real world is relevant enough that you want everybody to train on it. And then finally, as I mentioned, we're mostly working on DQN versus SEAC was obviously actor critic. That's in part a consequence of how we were focusing on off-policy algorithms. Now, for results, does it work? And the short answer is yes. This is one of the environments we trained at. You can see in green, in the middle here, a standard DQN. And in red, you can see 3 different variants of our super DQN algorithm built on top of DQN. And you can see they're both learning much faster in the beginning, and then they're generally also getting a higher performance toward the end of training. We also outperform a few other specific multi-agent algorithms, including, surprisingly, parameter sharing, which is generally considered to be doing pretty well. Before I go into more results, any questions so far?
Hey, I'm curious about the kind of variations of the super algorithm here, like the quantile, Gaussian, stochastic. What exactly is different there?
Okay, that's about how exactly we choose which experiences to share. I'll get to that in a few slides in more detail.
Okay.
Okay, then I'll move on. We see the same broad results in different environments. They're not always as clear as in the pursuit environment, but we generally see everywhere that super outperforms just the plain DQN. So the red is always doing better than green. And otherwise, it often trades blows with parameter sharing, even not always. So there's some cases where parameter sharing does better, but generally they're broadly comparable. And we've tried this in environments from the petting zoo packages. So those are the top 3 are relatively simple multi-agent test domains. We've tried it on a few different domains from a more recent DeepMind package called Melting Pot. So these are a bit more complex. And then we've also tried it on a couple of Atari variants where we could only really test one super variant against DQN, but we again see that super does a lot better than DQN. One thing that's interesting is that this uplift over DQN seems to hold pretty much everywhere. So some of the comparisons here depend a little bit on the environment, but one thing that's entirely constant is that we always do better than plain DQN, and that's not just across environments, it's also across different hyperparameters. So in this slide, I'm showing some of the environments from the last slide, just comparing the final performance of DQN and super, just for different hyperparameters. This was just something where we were hyperparameter tuning the plain DQN algorithm, and we saw that no matter what we did, adding this experience sharing on top always improved things. Even if the original DQN was doing really badly, we still got this performance uplift. The second thing that's interesting is, so I mentioned earlier we were looking at the selective sharing of experiences. And one obvious question is, well, is this just sort of a nice bonus that you're able to do this, or is it really key that you do this? And it turns out kind of both. So 2 things that are interesting in our results is, one, it scales down really well to very low bandwidths. So here in this figure, we're showing super with different bandwidths. On the left, just plain DDQN means we're not sharing any experiences. And then on the bottom here, we're increasing the bandwidth, the fraction of experiences we're sharing as we go to the right. And you can see that even with a very, very small target bandwidth, we're getting a significant performance uplift. So that's kind of nice. This super algorithm really scales down even to very low bandwidths. But what's even more surprising is that it doesn't just keep going up. Like you might think the more you share, the better, and the more bandwidth you have, the better. And you would expect that maybe sort of you get diminishing returns, but you keep increasing. But it turns out, at least in some environments, actually at some point there is not just diminishing returns, but it actually gets worse. So it can happen that sharing all the experiences is worse than sharing some experiences, and can even be worse than sharing nothing. So in this particular environment, you can see that sharing all the experiences on the right is actually doing slightly worse than not sharing anything at all. So really, it turns out that it's not just nice that you can scale down to low bandwidths, but it's actually important that you not share everything in some environments. It's not as clear in all environments. Sometimes you do just get diminishing returns, but you always see that even low bandwidths get an improvement. And this is especially strong early in training. So if you look, for instance, in the pursuit environment here, This kind of peak at low bandwidth is especially pronounced if you look at performance here. It's not as pronounced toward the end of training. So really, it's kind of nice. A low bandwidth especially helps you converge faster, which is nice. To answer Lucas's question, what are the 3 variants we have? So I mentioned earlier, we want to share some experiences, only the ones with the highest TD error, but what does that really mean in practice? We get experiences one at a time online, and so we need to decide for each experience individually, am I going to share this experience or not? And we came up with 3 different ways of doing that. The one which is actually not really a heuristic is to just keep a list of the most recent, let's say, 2000 TD errors. And when I get a new experience, I check, is it in the top C quantile of these last 2000 TD errors? So that way you really share the exact top C quantile. One reason you might not want to do that is that you have to keep this long list of recent TD errors, and then if you have to compute the C quantile, so you have to sort them basically every time. So the second thing we tried was, can we approximate this? So instead of keeping an actual list of recent TD errors, can we just keep a running mean and standard deviation of recent TD errors? And that's something you can compute very cheaply online. And then we pretend as if TD errors were a normal distribution, and we just share an experience that we just got if it's above the mean plus some number of standard deviation that would give you a C quantile. And then the third thing we tried was, can we just do this stochastically? Can we just sample? Can we decide for each experience with a probability that's proportional to the TD error, so that in expectation we share a fraction C, but for each of them we just flip a biased coin. And it turns out that quantile and Gaussian generally perform very, very similar. That also holds across all the environments where we tried all 3 of them. So this approximation with a normal distribution works really well. And interestingly, stochastic sharing tends to perform a little bit worse. And that's also pretty consistent across environments we tried. It's usually still doing better than not sharing at all, but it's generally significantly worse. Does that answer your question, or do you have any follow-up questions on that?
Yeah, it does answer my original question. I would be curious if you have any thoughts in terms of why the stochastic is notably worse. I don't know, maybe even just having the recency bias of the experience that you potentially share in the quantile can help, I would imagine, but I think all these things are maybe a bit more tricky to identify.
So we did, okay, that's actually perfect because that's my next slide. So we did try as well to look at this a little bit more. One way you can think of the difference between quantile and stochastic is that it's a different weight on deterministic versus randomized. In original PER, you have a similar thing. You have this parameter alpha that controls how strongly you prioritize things. Basically, in PER, you don't just sample proportional to the TD error, you sample proportional to some power of the TD error. So if alpha equals 1, then you just sample proportional to the TD error. If alpha equals 0, you would just do uniform random sampling from the replay buffer. And if you went toward infinity, you would sample deterministically just the top TD errors. And that's sort of the same principle that applies in super. In stochastic super, we basically did this with alpha equals 1. Quantile, you can basically consider as equivalent to setting alpha to infinity here, because then you just sample deterministically the top TD errors. You could also look at what happens if you set alpha to 0, so you do uniform sampling. And we tried this in an ablation study And it turns out if you do uniform super, so you only share a C fraction of experiences, but you just pick them randomly, uniform, that does badly. It does worse than deterministic, that's on the left here. It also does worse than stochastic. We don't have it on the plot, unfortunately, but it would be somewhere in the middle here. It can even do significantly worse than not sharing at all in one environment, like way, way, way worse. So you really see that going from deterministic with good performance to proportional to TD error, it gets worse, and uniform does really badly. So this extends even further. We don't know exactly why. It's actually a little bit surprising because in PER, it's actually important that you do this stochastic thing. In PER, if you just sample the top TD errors deterministically, that does worse than if you do the stochastic sampling. And for us here, it's the opposite. One reason intuitively why I think this happens is the following. In PER, the reason why you want to do stochastic is that if you do deterministic, there's going to be many experiences that you never look at. So if you do deterministic sampling in PER, anything that's not in the top TD errors, you never look at it ever. And that's kind of bad because there's a possibility that some of those experiences are really relevant. And then super, in a way, that same reason might lead you to want to do stochastic, to do deterministic. In super, you only ever consider the experience once, right? In PER, you in a replay buffer, you keep sampling over and over. So if you only ever look at the top ones, there's lots that you could have looked at some point, but you never look at them, even though you keep sampling. In super, you look at the experience once. So if this one time I look at the experience, I do stochastic sampling, and I discard it, even though it had a high TD error, I never get a second chance to look at it. And so really, my intuition is that what you really want to avoid is missing out on relevant experiences. And in super, that means that you want to be as deterministic as possible because you never look at this high TD error experience again if you have a random coin flip and you discard it. It might be that there is a middle ground somewhere where you have a very high alpha that's still finite, but bigger than 1. We didn't have a chance to run that many ablation studies, so we didn't check this out. It might also be that if you kept considering experiences more than 1 on the sender side, things would change. But my intuition is really that you want to make sure you don't discard something that's relevant, basically. Does that make sense?
Yeah, I think that pretty much answers my question.
Awesome.
I just wanted to chime in as well, like on when you made the remark that the earlier in training, it seemed that the difference was a lot more than later on. Is that something I also noticed in single agent RL when you use stuff like, for example, prioritized level replay, where you are sampling different instances of the environment. Some of them can be a bit outside of the distribution you want to generalize to. And those ones, if you have if you set the coefficient to be very high initially in training, the agent really struggles with having these out of distribution experiences to train on when it's really early, and it never really recovers. But if you do it really in the later stages, it is able to handle that much better. So it seems to be a similar mechanism, but I'm not exactly sure why this is the case, though.
You're saying that in PER, if you increase alpha later in training, it works?
No, it's more like the proportion of the experience that is outside of distribution. I saw that like right? That proportion for you is going to come from other agents, this experience, right?
Mm-hmm.
And in my case, it's coming from the single agent, but evaluated in environment instances that are a bit out of the distribution.
Mm-hmm.
So kind of like the instances you would get with domain randomization, for example.
Mm-hmm.
So those ones, they can hurt quite badly the agent's performance if you have too much of a fraction of this experience that is in your training data. So basically out of distribution.
Oh, interesting. But you're saying that for your case, that's more of a problem early in training?
Hello? I think I've lost the
I
connection.
think you froze for a second. Or I did, I guess.
Oh, okay. I don't. But basically, I was just saying that the out of distribution data early on in training, it really hurts also in single agent RL. So it seems to be a similar mechanism.
The opposite of what we are seeing here. So we very generally see that super helps more earlier in training than later in training. So that's interesting. That's again kind of the opposite than the single agent case then.
But didn't you show that when you have the share all, so when you have a very high proportion of out of distribution data,
mm-hmm.
that maybe I'm confounding things, but
yes,
I thought you said that like it's
point. That's a good point for sharing everything. This drop as you share everything, that drop is bigger earlier in training, I think. Although the slight caveat here is we didn't manage to like look at in this level of detail at like all the different environments. So it might be, I don't know how much that would generalize to every environment. But definitely in the one where we ran this ablation study, it was very clear that the drop was bigger earlier. Or at least sort of the peak in the middle was the biggest earlier.
Right. Yeah. Well, that's what I observed in single agent RL as well. So that's really interesting. Might be some follow up to do to look at. It seems very something I want to look into a bit more as well.
Yeah, I mean, our intuition here was that maybe if you share everything, it's too much irrelevant stuff and dilutes it too much. So it might also be that there could be some kind of hyperparameter tuning that makes this a bit better. We didn't really look at, for instance, changing the replay buffer hyperparameter. So you could also look at how this plot changes as you tune the alpha of the receiver's replay buffer. Could be that if you make the alpha bigger there so that you then more sample the higher TD errors, it might become less. I guess one of the practical problems with this work is that there's so many different ablations you could try that you just run out of compute power very quickly.
Yeah, absolutely. And also of space in your paper.
Yeah. Oh yeah, definitely.
Okay. That answers my. Thank you.
Okay. So yeah, this is pretty much what I had for the main talk. I thought it might be nice to have time for discussion as well. For a summary, our algorithm builds on top of existing DQN algorithms. One thing I didn't show in the figures now because they look very similar, but this works for different variations of DQN as well. So we tried both vanilla DQN as well as dual-link double DQN. And the performance gains are very similar for both. In principle, it should also work for other off-policy algorithms like SAC or DDPG. We might look at that in future work. We did some early experiments with them, and we did generally see a performance improvement as well. The main reason we didn't have it in the paper is that we just struggled to find good multi-agent environments where SAC, vanilla SAC, did okay. interesting conceptual contribution as well as this decentralized with communication training. So in principle, everything we do can run decentralized as long as you have some amount of communication bandwidth. And it scales down well to low bandwidth. So in principle, you don't need a lot of communication between the agents, and it doesn't really matter how little you have. It seems that even a tiny bit of communication can help. And by extension, one thing that's conceptually nice about the approach as well is that it kind of fails gracefully. If at some point, if you actually deployed this in the real world, and at some point during training, your communications channel goes down, nothing really happens. You could just keep training using standard DQN. Performance shouldn't explode randomly. Or similarly, if communications bandwidth is varying, you can just share as much as you're able to. And if at some point you share less experiences, nothing really happens. You could potentially even extend this to just sharing between agents that are near you and so on. It's pretty flexible. That's a nice thing because the idea is so simple. And then finally, we have code for this available on this URL. Hopefully also soon in RL Lab, we have a pull request open. And the paper is on arXiv and on NeurIPS. So thank you, everyone. Any more questions? I think we have time left for discussion, I guess.